Cappiello. They going to tell us about boosted like matter with cosmic rays.
Thanks so much for the introduction. Thanks for inviting me to come give a talk. Oh, it's just the being recorded thing. I'm Chris Cappiello, I'm a postdoc at Queens, and I'm going to talk about some work that I did partially as a graduate student at Ohio State, working with John Beacom, and then further continuing stuff that I'm doing on the same topic at Queens, all related to upscattering, sub-GeV or GeV-ish dark matter to high velocities and high energies. So let's start with what we think we know about the dark matter velocity distribution, and that is that it looks something like a Maxwellian halo. There's been a lot of work in the last several years prompted by Gaia data release 2, looking at kinematic substructure in the Milky Way halo. But in general, we still think it looks something like this peak distribution at around 300 kilometers per second, with a high velocity cutoff set by the escape velocity from the galaxy, which when you boost to the Earth's reference frame is around 800 kilometers per second. And this shape of the velocity distribution maps in an easily understandable way onto the shape of direct detection limits. What's this? If you want to probe relatively light dark matter, it means that that dark matter has to be moving relatively quickly. So if you're an experiment like LUX or Xenon, and you want to probe stuff that's down around a few GeV, you can only be sensitive to the high velocity tail of this distribution, where there's a relatively small fraction of the dark matter. And eventually, when you get too light, your limit just cuts off completely, because you would have to go past this escape velocity cutoff. There are several different ways that you can try to get around this problem. One is to just build detectors that are sensitive to lower recoil energies, and that's the strategy behind things like CREST. You can try to look for electron recoils, where you have matter scattering directly with electrons. You can look at things like the Migdal effect or Bremsstrahlung to try to push down to lower masses and lower energy thresholds. And that's all sort of on the detector side of things. But there's a completely different side that you could look at, which is there some way to produce dark matter that has higher velocity or higher energy than we normally think about with the standard halo model? And there are many, many ways to do this, and they range from having heavy particles annihilate to lighter dark matter states that then become relativistic. You can do this with purely gravitational effects, or you can do this with scattering between energetic standard model particles and dark matter particles to boost it up to high energy. And that can include supernova neutrinos, that can include energetic particles in the sun. But what I'm going to start out talking about is the collision between high energy cosmic rays, and dark matter. And this topic was sort of kicked off, as far as I know, by this paper by Brinkman and Pospelov a few years ago, where they used a relatively simple setup. And for that relatively simple setup, I have a relatively simple diagram. It's just that a cosmic ray comes in, collides with a dark matter particle, boosts that particle up to high energy. And in this Brinkman and Pospelov paper, they assumed that the cross-section between dark matter and nuclei, or dark matter and a nucleon, was just energy independent, was just a number. And they considered a spherical volume with a radius of a kiloparsec or a few kiloparsecs around the Earth. What you can do is basically multiply the dark matter density by the cosmic ray spectrum and the cross-section, integrate over the line of sight, and you get a flux of dark matter with very high energy reaching your detector. And they used this to set limits based on xenon 1 ton. They said, if this effect is happening, we should be able to see high energy dark matter in xenon 1 ton. Now, you'll notice the top of this exclusion region. The reason that this exclusion region doesn't just go up to arbitrarily large energies, or arbitrarily large cross-sections, is attenuation in the Earth. Dark matter interacts too strongly, it will collide with nuclei in the Earth's crust, or the detector shielding, or the atmosphere. It'll lose energy or get scattered away back out of the atmosphere, and it just won't reach your detector and be able to trigger it. Because of that, they also looked at mini-boon, and yes, mini-boon with a neutrino experiment, which you normally wouldn't be able to use as a direct detection experiment. But if you have dark matter being boosted up to relativistic energies, you can use neutrino experiments like this, and that's something I'll talk about a lot in this talk. Now, this paper kicked off lots and lots of work on this topic. There are lots of different directions you could go with this. One is to look not at dark matter nucleus scattering, but dark matter electron scattering. And that's what a paper by Ima et al. Did at almost the exact same time as this paper. And they set new limits on dark matter electron scattering, going down well below the sort of MEV-ish threshold that you would get from regular direct detection. You could also say, okay, this assumption that the cross-section is just a number is not really physically well motivated. Let's write down some simplified model and see what kind of cross-section you get out of that. And that's what was done in a number of papers, including this one that Professor Dutta worked on, where they also computed the analogous neutrino floor. And then this paper by Bondarenko et al., which looked at cosmic ray upscattering along with some cosmological bounds for things like EM, et cetera. We wanted to go a different direction. The sort of two directions that we went, there's one simple direction and one much more complicated direction. The simple one is just look at additional data sets, see are there other detectors we can use, other data sets from the same detectors to improve these constraints. The more complicated one is sophisticated modeling of attenuation in the Earth, which I mentioned a minute ago is the reason that that xenon limit cannot go up to arbitrarily large cross sections. So I'm going to start with the simple one of just looking at additional data sets. And I'm going to start here with the case of dark matter electron scattering, because attenuation really becomes more important for dark matter proton or dark matter nucleus scattering. So the way that you compute limits based on cosmic ray dark matter scattering is you need to start with the local interstellar spectrum of cosmic rays. We use the interstellar spectrum rather than the observed spectrum at Earth so that you don't run into problems with solar modulation, solar modulation. And basically you have this integral over the line of sight of the dark matter density, cosmic ray spectrum, cross section. And when you compute that integral, you get a flux of dark matter that looks like this. We've used a cross section of 10 to the minus 30 square centimeters. And then this is what the spectrum looks like for various different dark matter masses. Once you have this, you can take that spectrum from the spectrum of dark matter at Earth. You can do the same thing that you would do in a standard direct detection analysis, compute what the recoil spectrum looks like in a detector, and then set limits by comparing that to data. And that's what the Ima et al. Paper did. This is for a couple of different masses. This is the dark matter event spectrum that they compute in Super K. But they cut off their Super K analysis at an energy of about 100 MeV. And what we said is, okay, you can do that. You can get a limit from that based on data that's of 100 MeV. But if you notice, if you go down to lower energy, the spectrum gets larger. So is there data down at lower energy that we could look at, and can you get better limits from that? And to do that, we looked at data from a paper from 2011 that was a supernova relic neutrino search. And this data goes down to an energy that's almost an order of magnitude lower. And if we plot this data on the same axes as this sort of projection from the Ima paper, we get this. So this solid line here is for a mass of 1 MeV. This is the event spectrum that you would get at their sort of limiting cross-section, at the lowest cross-section they say that you constrain. And you see that that completely dwarfs the low energy data. So you can go down to lower and lower cross-sections and still have a spectrum that's above the data. Based on this, we decided to set a limit by requiring that we don't do any kind of fancy background modeling. all we do is say all of this data could in principle be dark matter events. We just say if the spectrum is at any point higher than the total background at the 90% level, we say that that mass and cross-section is ruled out. And by doing so, we're able to set a limit that's around a factor of 5 stronger than the limit that Ema et al. Got. And then we also set a projected limit from hyper K, assuming that they can do some sort of either background subtraction or profile likelihood analysis. Now, that was the first part of this first paper, and that was the very simple thing, just do the exact same analysis with different data. But now we turn to the case of dark matter nucleon scattering. As I mentioned before, there's the ceiling for xenon 1 ton, and that's based on the attenuation of dark matter in the Earth. If you want to go to higher cross sections, you can look at mini boon, but there's this gap between those two exclusion regions, and we asked, okay, is there some other detector that we can look at, something that's not as deep underground as xenon 1 ton, but that is deeper and has lower background than mini boon. And the experiment we settled on is another neutrino experiment, Dia-Bay, which is a anti-neutrino experiment with detectors distributed between 3 different halls. The shallowest of those is under 250 meters water equivalent, which is about 100 meters of Earth. So it's an order of magnitude shallower than xenon 1 ton, but it's much, much deeper than mini boon. So we thought just based on that, we might be able to get a constraint that sits right in between those 2 exclusion regions. Now, we need to take a little bit of a detour and talk about attenuation in the Earth and how attenuation is modeled. What Ringman and Pospelov used was something that I'll call the straight line approximation or the ballistic approximation. And that approximation says dark matter travels in a straight line through the Earth. Every particle scatters the average number of times, the same number of times. Every particle at a given velocity suffers the same amount of energy loss. And so you can compute an attenuated or reduced velocity spectrum based on that formalism. This formalism is well motivated for high mass dark matter. If you're looking for very, very massive dark matter that doesn't really change its trajectory appreciably when it scatters with a nucleus. But when dark matter is relatively light, this isn't really a good physical description of what's happening. Dark matter could scatter through large angles. And also, if dark matter has a mass that's comparable to the mass of a nucleus, you could lose a ton of energy in a single scattering. And so the total number of scatterings you need to slow it down is small, and then Poisson fluctuations start mattering. So the more proper way to model the attenuation of light dark matter is to write a Monte Carlo code that propagates tons and tons of particles through the shielding or through the crust and asks how many of them reach the detector and with what amount of energy. This plot is from a paper by Timon Emkin, and this is not at all related to cosmic ray scattering or boosted dark matter. This is just standard halo model dark matter passing through the Earth. And this blue line and yellow line are 2 different sort of implementations of a ballistic or a straight line trajectory. The green points are the result of a code called Damascus, which is a Monte Carlo simulation code that Timon wrote. And basically what this is showing is that as you increase the cross-section, you get more and more events in your detector as you expect until you get to large enough cross-sections that attenuation starts mattering. And then that sort of turns over. But what you find is that the maximum cross-section that you can reach with an experiment, in this plot at least, ends up being somewhat higher if you model this using a Monte Carlo code than if you do this simple ballistic approximation. That conclusion depends slightly on the setup and the depth and the energy threshold and things like that. But the general point is that you can get a noticeable difference between the Monte Carlo result and the approximate ballistic trajectory result. So what we decided to do was model attenuation, not using the ballistic approximation, but write our own Monte Carlo code to model this propagation. Now, there are a couple issues you run into doing this. One is that, as far as we were able to find, there are no Monte Carlo codes out there that include full relativistic kinematics that we would need for this. So we had to write our own Monte Carlo code to do this propagation. Another issue you run into that's more subtle is that typically when you model attenuation or when you compute direct detection rates or what have you, you're just looking at elastic scattering. And the cross-section for elastic scattering depends on the so-called form factor, where that cross-section ends up being suppressed at very large energy transfers. This is totally fine as long as the scattering is always elastic. But the problem that you run into is that when you have these high energy relativistic particles, there can be inelastic effects, there can be quasi-elastic effects. None of that is captured if you just include the elastic cross-section and let it go to zero or become very small because of that form factor suppression. And so if you just do this the standard way of just having the elastic cross-section, which has a form factor in it, you run the risk of assuming that the total cross-section is very small, when in fact it's not small, it's just that you've ignored the inelastic effects which are dominant. And so what the Brinkman and Pospelov paper did was they ignored the form factor when computing the mean free path. They still included it when computing the average energy loss, but they didn't include it when computing the mean free path. We decided to take the same approach. We write a Monte Carlo code that does full three-dimensional propagation, unlike the straight line approximation, but we still use this assumption that we just don't let the total cross-section get too small. We also cut the dark matter spectrum off at 1 GeV in order to be in a regime where it's at least more reasonable to ignore inelastic effects than if we were allowing things to go up to 10 GeV or what have you. I fully recognize that this isn't a perfect physically correct picture of what's going on, but we decided that it's a conservative way to make sure that we're not accidentally overestimating the mean free path by a gigantic amount. Now, what you end up with when you do this Monte Carlo code is this plot. So for a second, I want you to look just at the two solid lines. These are both for the same cross-section, but using the ballistic approximation and our numerical code. And you can notice a difference between them, but they're like within an order of magnitude or so. But when you look at large cross-sections, you start seeing a gigantic difference. With the ballistic approximation, you have a flux that's very high at low energies and then has a sharp cutoff. This is basically, this is something that you see somewhat generically with this ballistic approximation because everything loses the same amount of energy. So if you started off with a spectrum that cut off or became very steep at some energy, that energy just moves down. But with our Monte Carlo code, there are some particles that scatter fewer times. Particularly with high energy, there are particles that have large momentum transfer. And so the form factor that we do include in the angular distribution leads them toward very forward scattering. And as a result, you get a lot more events at high cross-section using the using the Monte Carlo approach than you would get with the ballistic approximation. And based on all of that, we do the same thing that we did for electrons. We just say that if at any point the dark matter induced event spectrum is larger at a statistically significant level than the total background, then that dark matter mass and cross-section is ruled out. And by comparing to this diabase data, we're able to set a large exclusion region that sits exactly where we wanted it to. It doesn't go as high as the ceiling of Miniboon because there's more shielding. It doesn't go nearly as low as Xenon 1 ton does because there's way more background, but it sits right in the middle where we wanted it to. with all of this machinery in place, we said, okay, why not look at other detectors? And we looked at CAMLAND, another neutrino experiment, and we were able to set a limit that covers a lot of the same parameter space that the xenon one-ton exclusion region did. And then finally, the last thing we did in this project was to set projected exclusion regions for a number of other neutrino experiments. One being Juno, which is currently under construction, and this is assuming that they could do some level of background subtraction or fitting to the background data. The other was for Prospect. Prospect is a reactor neutrino experiment that's located basically at the surface of the Earth in Oak Ridge, Tennessee, at Oak Ridge National Lab. It has even less shielding than the mini Boone experiment. The problem is it has tons and tons of background. So we weren't able to set an exclusion region based on it immediately, but we thought, if there are ways that they can do background rejection through things like pulse shape discrimination and fiducialization, et cetera, you might be able to reduce the total background rate by multiple orders of magnitude. And if you do that, there's some region up here that you would be able to exclude. These two dashed curves are just sort of a conservative and more aggressive estimate of what that exclusion region would be. And that takes me to the next part of my talk. Are there any brief questions anyone wants to ask about sort of the setup? Okay, so next I'm going to move on to.
Sorry, do you have a projection for like generation for dark matter? So on what time there, right?
We do not, but there's a recent paper by like Ranjan Laha and somebody that did this for LZ and then set projections for Xenon N-ton or Darwin that just came out like in the last couple weeks.
There's like some white space not far.
Right, so we didn't look at this for anything like Darwin or Xenon N-ton or anything. There is, like I said, there is another paper that did that, but it's quite recent. It's like in the last few weeks. So with this projected exclusion region in mind, we got in touch with some members of the Prospect collaboration and basically said, hey, do you want to try to constrain dark matter with your detector? And they said, sure. And so the next part of my talk is going to be based on an analysis we did along with members of the Prospect collaboration. The data analysis on the Prospect side was led largely by a graduate student named Manuel Andrea Murata, along with his advisor, Bryce Littlejohn. So this is a picture of Prospect. It's a 4-ton neutrino experiment, which is gigantic in my mind as a dark matter person, but fairly small compared to the other neutrino experiments we've been looking at. And again, it's at the surface of the Earth. It has even less shielding than mini Boone does. The shielding is basically the atmosphere and what you see in this picture here. The problem, as I mentioned, is that the data, the total background rate, even when the reactor is off, is relatively large. And so Manuel's job in this project was to take this, and the rest of the Prospect collaboration was to take this total event rate and reduce it down to something more manageable. And they did this through a variety of cuts. The first one was to only look for single pulse events. We're looking at large cross sections, but still small enough that dark matter shouldn't scatter several times in the detector. So they're looking for single pulse events. They did a pulse shape discrimination cut and then fiducialization of the detector. In my next slide, I'm going to go through a couple of these just to explain how they work. The fiducialization part is over here. So this is sort of a cross section of the Prospect detector. It's made up of a bunch of basically long rectangular tanks of scintillator. And what you see from the scale on the right here is that there's a very high event rate on the outer regions of the detector, and it's much lower in the center. So they basically cut out the outer few regions, and then for each one of these tanks also cut off basically the end of them for the analysis. The pulse shape discrimination, if you're not familiar with this concept, the idea is that in a scintillator like this, when there's a nuclear recoil or an electron recoil, it produces light, which is observed by the PMPs, but it's not an instantaneous spike. There's sort of a rise time and then a long fall off. And the shape of that pulse depends on what kind of recoil it is. The band down here is electron recoils. This intermediate band is is proton recoils. And then I don't know how well you can see it in the light. There's another band up here that's higher A nuclear recoils, things like carbon. And so what we were looking for in this project was just proton recoils. So you can see from this scale here, there are tons and tons and tons of electron recoils. And using pulse shape discrimination, you're able to cut almost all of that out, which reduces the total background. But unfortunately, even with all of those cuts, that background is still relatively large compared to the flux you would get with some of the masses and cross sections that we wanted to look at. So we asked, okay, is there something else you can do to cut out or discriminate between a dark matter signal and your standard model background? And one thing that we thought of, this is something that I think Professor Strigari brought up at lunch or at the journal club, is daily modulation, because these cross sections are so large that, we've been talking about attenuation in the Earth's crust, and mostly we've been talking about attenuation of dark matter that's just coming from overhead, going through the atmosphere and a little bit of Earth. But dark matter coming from the opposite side of the planet would be completely blocked. There's way, way, way more Earth on the other side, which means that as the Earth rotates, if the flux coming in is not completely isotropic, that event rate will change over time, over the course of a day. And because this dark matter is being upscattered by cosmic rays just throughout the galaxy, most of the flux is going to be coming from the direction of the galactic center, right? Because that's where the highest dark matter density is, and that's also where the largest sort of line of sight is that you can go through and still have dark matter and cosmic rays. And so what we did here, and this was, I think, the most difficult thing that Manoa had to do, was bin all of the data in, we used 16 live days of prospect data, get to bin all of this data by hour, but not by solar hour, by sidereal hour. So sidereal time basically accounts for the fact that if this is the sun and the Earth is orbiting around the sun, if you start at a time of day where the sun is directly overhead, and then the Earth rotates, and the next day you're at a point in time where the sun is directly overhead, you're not actually looking the same direction, right? Because the Earth has moved a little bit along its orbit. So the difference between solar time and sidereal time takes account for the fact that as the Earth goes around the sun, the direction of the sun changes a little bit. So Manoa had to really precisely compute the direction that the detector was looking, or the direction of overhead, as a function of time as the Earth was moving around the sun. So it was a complicated analysis that I helped with some, Manoa did most of the work, and then with our propagation code, we set it up in a way to basically compute how much dark matter is coming from a given direction. So dark matter coming from, near the horizon gets attenuated a lot. Dark matter coming from directly overhead gets attenuated less. And so based on this, we can compute what the spectrum would look like for dark matter, and that's what's shown in this red line and light blue line. These are just for two different cross sections for the same dark matter mass. You see a daily modulation that looks like this. And if you look at the data, you don't see that modulation. If anything, you see something that has slightly the opposite sign. And the reason for that is this dashed line here is data from is based on data from the cosmogenic phytos. So they actually know that there's a very slight time dependence of their cosmogenic backgrounds. So by comparing a dark matter signal that looks like this with a cosmogenic signal that is mostly flat but slightly tilted in the opposite direction, we're able to rule out a very large area of parameter space that not only goes above the mini boon exclusion region, which is what we were going for, but also cuts down into that same region between the xenon 1 ton and mini boon exclusion regions. So this is sort of the end of the first part of my talk, where I talk about cosmic ray scattering. But the point is that there are all sorts of directions that you can go with cosmic ray dark matter scattering, looking at different models, different detectors, different ways of modeling attenuation, and all sorts of other things that I haven't even touched on. What questions do you guys have before I move on to something that's in a little bit different direction? Yeah.
Could you just explain the data again from the previous?
Yeah. Just why it has this sort of bump like this. So what we initially expected was that the data would be completely flat in time. And what we actually found was that it has a little bit of a daily modulation in it. The reason for that is, as it turns out, the rate of cosmogenic background, so this is stuff from, cosmic rays hitting the atmosphere and showering and producing neutrons and muons and things like that, does have a slight time dependence to it, which is, this is something that they found using their, for example, muon vetoes, things that would not be triggered by this dark matter. So, they know that that rate is something that's coming from standard model backgrounds. And then they look at the data and they see that, okay, the data we observed in the detector roughly follows the time profile of what they saw in that cosmogenic veto. Does that answer your question?
So what's the mass of this detector?
It's, the total mass is 4 tons. The fiducial mass, so that includes things like shielding and housing. The fiducial mass that we used, I think, ended up being a little bit less than a ton. I can check for sure with my doc.
I know you have to go where the detectors are, but looking at the galactic center, the hemisphere is really lousy place to look for. So how much does the atmosphere affect this detection?
The atmosphere affects it a lot because, this detector is on the surface of the Earth. So this ceiling right here is basically due to the atmosphere. So if we had a position where we could look more directly at the galactic center rather than it being, uncomfortably close to the horizon, we could potentially do much better, although that could also potentially mean that at this hour of the day, not as much of the flux is blocked by the Earth. So I don't know off the top of my head how much you would gain. You could certainly go to larger cross sections, but you might not have as much discriminating power based on the time delay or the time modulation. All right, I'm going to talk really briefly about a topic I brought up earlier in my talk, which is that if you just assume that the scattering is elastic and you use the form factor the way that you normally would in direct detection, you can end up in a situation where you're assuming that the total cross-section is very, very small because you've avoided talking about any inelastic or quasi-elastic effects. And this is, for example, what was seen in at least one analysis that was done a while back. But then just in the last couple months, there was a paper by Alvey et al. Where they did something really neat. They said, okay, we don't really know what all these inelastic effects would look like for dark matter, but there are codes that will do this for neutrinos that'll compute deep inelastic scattering processes. So what if we use these codes to compute cross sections for deep inelastic scattering processes, and then map those onto our dark matter model and asked what attenuation looks like then. And they ended up with a really cool plot here, where so this is from a previous direct detection analysis, where they said, let's use the form factor as you normally would, and the ceiling that they get is up here. It's just gigantically high because, again, for this high energy dark matter, the form factor suppresses the total cross-section, which suppresses attenuation. What this more recent paper said was, okay, if you do that and don't include inelastic scattering, you get something that's gigantically large. But if you include inelastic scattering, or if you include high energy cutoff to your flux, you get something that is much closer to what was obtained by the original Brinkman and Potsvalov result, and similar to what we obtained here for CAMLAN. So what that means is that the way we modeled attenuation, I admitted, was not 100% physical. There were some assumptions we made in order to be conservative, but it actually seems like, if you go back to our CAMLAN result, which is the same depth underground as xenon 1 ton, we got something that sat right around here. It looks like when you include all of those inelastic effects properly, you get something that's reasonably similar to that. So again, we're not claiming that this is totally physically correct, but it means that the assumptions that we made were reasonable and well motivated. Now I'm going to change gears a little bit. I'm going to talk not about scattering with cosmic rays, but scattering with energetic particles in supernova remnants. So why would we want to do this? Well, supernova remnants expand at expansion velocities upwards of 0.01 c, which is an order of magnitude larger than typical dark matter velocities in the halo. There's also just a lot of mass. There can be several solar masses worth of ejecta mass. So that's a lot of nuclei to collide with dark matter, which makes this idea a cool other direction to go other than looking at cosmic rays. Unfortunately, there are a couple of problems with this. One is that supernova remnants are far away. The closest ones are a couple hundred parsecs away. The other is that supernova explosions are transient events, maybe not transient on the time scale of human lifetimes. They can expand for thousands or tens of thousands of years at very large velocities, but transient compared to the lifetime of the Milky Way. So we know there was a supernova explosion nearby 1 million years ago. It won't still be expanding at the same rate today. Now, when I say supernova shocks upscattering dark matter, I want to add a little asterisk. I'm not talking about Fermi acceleration. There are some papers people have written about millicharged dark matter getting accelerated in supernova shocks in the same way that cosmic rays get accelerated in supernova shocks. It's a super cool topic in its own right, but it's not what I'm going to talk about here. We're just talking again about elastic scattering between nuclei in the shock and ambient dark matter particles near the supernova. Now, because of this transience of the signal, we need to look carefully at what supernova remnant we consider. Because if we want to look at something relatively nearby, but it's very old, then all of the dark matter that it upscattered when it first exploded would have flown past us by now. Similarly, if it's too young, then the dark matter might not have reached us yet. Luckily, there is a nearby supernova remnant that works very well for this, and that is the monogem ring. Monogem, we think, is the result of a type 2 supernova that is around 300 parsecs away, and the most recent estimate of its age is about 68,000 years. What that means is that particles traveling around 4,300 kilometers per second, if they were produced when the explosion went off, would be reaching us approximately today. In order to really understand how this happens, we need to model the velocity of the supernova shock and the size of the supernova remnant as a function of time. These equations both come from the Sedov-Taylor blast wave solution, which is the way that supernova explosions are typically modeled. You need a few inputs for this. You need the supernova energy and the mass of the ejecta. We assume an ejecta mass of around 5 solar masses. And the supernova energy, this is something that has been calculated based on observations and is also in line with the standard, approximately 10 to the 51 erg energy that you expect to see from a supernova. We also need to know what the ejecta is made up of, because say, for example, we're looking at standard spin-independent scattering. The dark matter cross-section on hydrogen is going to be different from the cross-section on helium and oxygen, et cetera. These abundances are not actually taken from observations. It's something that's difficult to do for a particular supernova. But these are taken from a suite of simulations that were performed of type 2 supernovae with various progenitor masses. And we've basically averaged over a bunch of the results to get the abundances of different nuclei. With these abundances and with the size of the shock and velocity of the shock as a function of time, we can write down this big integral, which is similar to one of the formulae that we had for cosmic rays. You basically have the dark matter density, the velocity of the shock. This is sort of the mass of the ejecta broken up into the various nuclear components and then the cross section. And this formula gives you the velocity spectrum of upscattered dark matter at a particular time in the supernova's evolution. That's what's shown here. These individual peaks come from different nuclei because, for example, an iron nucleus traveling at a certain velocity can impart more energy to a GeV dark matter particle than a proton traveling at the same velocity can. For simplicity, we assume that all of the ejecta is traveling at approximately shock velocity, which isn't 100% true, but that's where the density peaks, and that's also the part of the supernova remnant that has the largest sort of geometric 4 pi r squared factor. So this is like maybe a factor of 2 error in the total result. So this is what the spectrum is that's upscattered by the supernova remnant at the supernova remnant itself. If you want to know the spectrum that arrives at Earth, you have to notice that only one velocity, one sliver of this plot will actually be reaching the Earth today. If it's too low velocity, it won't have reached us yet. If it's too high velocity, it will have just flown by us. And so to compute the spectrum reaching us today, you need to take that same integral, integrate it again over all time, over the age of the supernova remnant, and then throw in a delta function that basically requires that the velocity you pick out at a particular age is the velocity that would be reaching us today. And when you do that, you get a spectrum that looks something like this. Now, the total flux here is very small. It's something like 10 to the minus 7, 10 to the minus 8 particles per centimeter squared per second. It's something that, if all of these particles interacted any time they went through a detector, you might be able to see this with the xenon 1 ton or something, but it's a very small rate. And this is for a cross section of 10 to the minus 30 square centimeters and a mass of a GeV. So if we look at how that compares to existing limits, that's sitting like right in the middle of a bunch of direct detection limits. And if you want to go to larger cross sections than that, then you have to contend with cosmological limits, things from the CMB and structure formation and Milky Way satellite galaxies. So as a result, this doesn't really work. It was a cool project idea. Thanks for coming to my talk. No, I'm joking, I promise. This was basically the status of this project a little bit before I arrived at Queens as a postdoc. But then I realized, we're looking at a process that gives you very high velocity dark matter. And there are models that will give you, or there are effective operators that will give you strongly velocity dependent cross sections. So what I'm going to describe here is a framework that's known as non-relativistic effective field theory or non-relativistic effective operators. this idea, sort of in the form that you see here, was written down in some work by Haxton and Fitzpatrick, maybe a decade or so ago. And the idea is to write down in terms of Galilean invariant quantities any possible non-relativistic reduction of a fully UV complete model that you could write down. In other words, any model that you want to write down for dark matter, when you turn it into a non-relativistic cross-section, that cross-section will depend on some combination of these operators. And a couple of these are things that if you do dark matter direct detection, you'll be familiar with. O1 here is the standard spin independent scattering. O4 is what we usually call spin independent, or sorry, O1 is spin independent. O4 is what we usually call spin dependent. And both of those produce cross sections that are velocity independent. But what you see is that all these other operators produce cross sections that are strongly velocity dependent. And what that means is if we're looking at a process that takes place at large velocity, we might be able to probe some of these much more strongly or much more competitively than we can probe the standard spin independent case. Now, in particular, we're going to look at these three operators, O3, O6, and O15. O15 because it's the one that scales as v to the 6, so that's sort of the best you could possibly do. And then we choose two other representative operators that give cross sections that scale like v to the 4. There are limits on some of these effective operators. There are limits from cosmology and astrophysics, and there are a lot of constraints from direct detection experiments, but most of these are at relatively large masses. When I say relatively large, I mean above a few GeV. There are a few limits that go down to sub-GeV parameter space. This is from CREST 2. This is from one of the CDMS runs. But most of the direct detection limits are sort of at masses that are too high to be relevant if we're looking, as we did with the cosmic ray stuff, at low mass sub-GeV dark matter. Now, this was sort of an idea that I had in my head when I was applying to come to Queens as a postdoc. And I talked to Aaron Vincent about this and said, hey, you know stuff about dark matter scattering in the sun and velocity dependent dark matter scattering. Do you know how to model this for a supernova remnant or anything like that? And he said, this is perfect timing because my student Neil just finished writing a code that models the capture of dark matter in the sun in exactly the same non-relativistic effective operator framework. So sort of the meat of this project was taking this code that Neil had written and rewriting parts of it so that it would model not dark matter downscattering to the point where it would be gravitationally captured, but upscattering due to collisions with energetic hydrogen and helium and other nuclei coming out of a supernova shock. Once we do that, we can compute the spectrum of dark matter that reaches the Earth, the velocity distribution of dark matter that reaches the Earth. We need a detector to look for this stuff. And one of the interesting things about any of this upscattered dark matter, be it cosmic ray upscattered or supernova upscattered, is that your event rate actually scales with two factors of the cross section, right? There's one factor for the upscattering itself and one factor for the dark matter to be detected. Because of that, you gain a lot more by looking at large cross sections or large couplings than you would for standard direct detection. But at the same time, if you make the cross section too large, then you have to worry about attenuation. Because of that, we wanted to look initially at surface detectors, dark matter detectors that exist at the surface of the Earth, and as a result can probe relatively large cross sections. And the detector that we settled on was what's shown in red here, this super CDMS surface athermal phonon detector. This is a detector that had a total exposure of only around 10 gram days. So it's relatively small compared to something like xenon 1 ton, but it can get up to really large cross sections. And despite that small exposure, it's able to set good limits. This is from a CDMS paper. So this is, the limit that they set on standard halo model dark matter. So we wanted to ask what kind of limit can this set on supernova upscattered dark matter. So what you're seeing here in blue is the data from that super CDMS surface detector. In order to set their limits, they didn't do any kind of background modeling or profile likelihood analysis. They just used what's called the optimal interval method, where you basically assume that any of these events could be dark matter events, and then work out what is the optimal energy range over which the signal is largest compared to the background. We did the exact same thing using the spectrum of upscattered dark matter produced by supernovae, and that's what's shown right here for a mass of 1 GeV and a coupling that's sort of the smallest coupling that is ruled out by this data. So this curve is just barely too large to be consistent with the data. We computed this spectrum using a code called WIMPI and REFT, which was written by Bradley Kavanaugh, which models detector responses for all these different effective operators. So based on this comparison between the data and the dark matter spectrum, we're able to get an exclusion region on this operator O15, where the solid dark red here is our exclusion region from that surface detector. But you can also look at other detectors or other future detectors. It turns out that if you look at existing deep underground detectors, you can't quite get a limit out of them. But this is a projection that we set based on a super CDMS detector, or series of detectors actually, that are planned to be installed at Snow Lab in the next couple years. So this is something that in the very near future, there is going to be data that would be able to constrain this. And just to give you sort of an idea of how useful the supernova upscattering part is, the expected or projected sensitivity of that super CDMS detector goes down to around half a GeV. We're able to push that down to a little bit under 100 MeV by looking at this higher velocity dark matter. And then if you want to look very far in the future, this is the exclusion region that you could get from a future xenon-based detector like Darwin, which, if you look at detectors like Xenon 1 ton or Lux, they generally cut off at masses up around 5 or 6 GeV. So we can also push that down by a factor of a few. Now, this was for the operator O15. You can also look at a couple of these other operators. This is O3. The weird gap in the middle of this exclusion region is just due to a fluke of the data. It just turns out that for this particular dark matter mass, that red dashed curve that I showed here to the data is never high enough to set a limit. But again, that was using this optimal interval method where we assume that all of the events are potentially due to dark matter. If you did any kind of background modeling at all and did some sort of profile likelihood fit, that would go away and you'd be able to set a large solid exclusion region here. These projections are again from a future super CDMS and xenon-based detector. Same thing here for 06, but you notice that you don't see the same solid red region. The reason is that 06 you can think of as basically a velocity-dependent version of your spin-dependent scattering operator. And for spin-dependent scattering, you don't get any response from silicon, which is what this detector is made of. So we couldn't use this detector at all. But then we got to thinking, okay, Pico exists. And this isn't ideal because Pico is deep underground, whereas we were initially hoping to look at surface detectors. But it is optimized to look for spin-dependent dark matter. So we did an analysis based on the most recent Pico results, and it's not a huge exclusion region, but there is an exclusion region there that you can set. And by the way, I want to emphasize that the y-axis on this plot is gigantic. It's 15 orders of magnitude. So these are these regions are wider than you might initially expect.
So, but the solid line is the surface.
Yeah,
So
solid.
why is it discontinued?
Yeah, this is, so if you go back here, this is sort of for a small coupling. When you make the coupling larger and larger, two things happen. One, the peak gets higher, and two, the peak moves further to the left because of energy loss. So for most masses, the peak, follows something like this. So there's a range of couplings for which it's significantly above the data. For that particular mass, for that operator, the peak follows something like this. So it always sits just barely below the data. And again, if we were able to do any kind of background modeling at all, that would go away because then a peak this high would be more than sufficient to set a limit. But it's just a fluke of the data combined with energy loss for that particular mass. So this is the result that I'll leave you with. The conclusion is that this idea of upscattered dark matter has tons and tons of different directions you can go with it. There are lots of limits we can set on different operators based on existing detectors, and there's also a lot that you'll be able to do in the near future with detectors that are currently under construction or will be under construction very soon. Before I finish up, I want to thank a couple people. One, I want to point out again that the prospect analysis was led largely by a grad student, Manoa Andrea Murado. I want to point out that in our initial version of our propagation code that we used for the Supernova, for the cosmic ray project, there was actually a numerical bug that was found by Kazumi Hata, who is a grad student at Tohoku University, who was working in their CamLand group and was interested in comparing to our results. And then I also want to thank Bradley Kavanaugh, because when we initially started the Supernova project, his WinPy code that we used to compute recoil spectra only supported some of the operators. It was only the first like 8 or 10 operators in that list I showed you. And we emailed them and said, hey, are there any plans to include some of the others because we're interested in using it? And he said, sure, I will do that right away. And he did. So thank you to him. And thank you to you guys for inviting me to give a talk, because I graduated during COVID. And so this is the first time that I've been invited to actually get on a plane and physically give a seminar somewhere. So thank you guys very much. Yeah.
You focused on one supernova, many supernovae.
Yes.
So what does the capitalizing of all the supernovae affect what your conclusions here?
Right. That's something that we want to look at. I worry that, there are tons of supernova remnants out there, but there may be relatively few that have the right sort of ratio of age to distance to actually give a large signal. There were a couple other supernova remnants that we thought about using before we settled on monogem, but there are not a ton that are relatively close by and have the right age. So yeah, it's something that we've been talking about looking at the very least, but I'm not super optimistic.
Very question, so for the first part of your talk, it's just like the ambient cosmic rays, right?
Yes.
So where do they are they local? I know you said they're outside the heliosphere, I think, right?
Yeah.
Are they, do you know, to get a sense of the appropriate convolutions, are they where are they? Where are you getting the dominant components in the cosmic ray galaxy, and at what energy are they coming from?
The limits, yeah, great question. The limits are dominated by the nearest sort of kiloparsec or so. If you go outside of that, so we include roughly the full galaxy. We consider the cosmic ray halo to have a radius of 10 kiloparsecs and a height of 1 kiloparsec. We consider that entire volume, and when we do that, we get limits that get stronger by a factor of 2 compared to just doing the nearest.
So practically, I guess like what the Voyager results now for like
Mhm.
cosmic results that type of thing.
Yeah.
You don't need to go to like Alpha.
So what we used, this black curve on the left here, black dash curve, is what we used. That's the local interstellar spectrum computed using Galprop. This is from a series of papers on something called HELMOD, which sort of takes Galprop and sees what the effect is of solar modulation and tries to fit that to existing cosmic ray data. This is a series of papers by Bush-Meany et al. From like 2017, 2018. So we use a predicted flux, but it's a predicted flux that matches very well both with observed data on Earth at high energy and with Voyager data at lower energy.
So that's the cosmic data.
Yes.
Contributing to this.
Yeah, and we did look a bit into how the energy and the flux is thought to vary as a function of, how far you are from the galactic center. And it's not gigantic, it's close enough to uniform that we modeled it as being uniform. That's, if anything, a little bit conservative because it might be a little bit harder toward the galactic center. Other questions?
If you have like, I mean, so the problem with like these directional dark matter detectors, it's too small, like that competitive.
Mhm. Yeah.
I mean, if you like have one of those, I mean, like your cross sections are huge, you're talking about,
Mhm.
so you get some level mitigated by that. If you thought about like, let's say if you had to or something like that, put it underground, like that. With that editing this, because you talk about the time modulation. Right?
Yeah,
Identifying these particles, right? You could actually get a sense of the direction of the particle. Usually it's
yeah, yeah. So I mean, that's that's sort of what we were trying to simulate in the Prospect project by just saying stuff coming from this direction is blocked, stuff coming from this direction is blocked less, so that you get a modulation. There are people who have thought about how to get, basically, if dark matter is very strongly interacting, you can do away with the need for a directional detector just by looking for this kind of daily modulation. I don't know if that's your question.
kind of, but yeah, so you're basically asking it's not really.
Right. I mean, I think this.
Yeah. So, yeah. And sensitivity, I guess I can imagine doesn't help with
Right.
I mean, you've already got the time, I guess. Oh, yeah, okay.
Yeah, I mean, if you had, so for lower cross sections where you don't have to worry so much about attenuation, a directional detector could definitely allow you to do what we did with Prospect, but without relying on the attenuation effect. But then I worry that the size of the detector, the total exposure just wouldn't be nearly enough.
So how much cosmic ray is there in terms of sensitivity?
Cosmic rays are definitely better in the sense that
Because it would be a background for you.
oh, you're saying cosmic rays would be
Yeah, because cosmic ray is doing that all the time. Supernova comes and does it for the time. So how do they know that they really you are getting it from supernova? And hence,
right. So there are a couple ways to answer that. One is that this signal lasts for a very long time, because if you go back to the velocity distribution at the supernova, there are some very low velocity particles, some very large velocity particles, and the supernova is expanding for thousands of years. So the supernova upscatter signal is not going to be transient the way that neutrinos from a supernova are. It's going to be relatively constant. I don't know if that's part of your.
That's okay. So that means that it always is.
Right.
But now then, how do I know like what I'm seeing? Is it the cosmic ray boosted or super?
Right. Part of the answer is we don't know, and that's why when we set our limits, we just required that the spectrum be larger than the total, like the total background event rate that is seen in the detector. If you could do better than that with some modeling of the standard model backgrounds, but then, right, if you saw like a particular bump above the standard model background, is that due to cosmic ray scattering or due to supernova upscattering? You would have to compare the energy spectra that you expect, but probably, especially if you don't have great statistics, you would probably, there would be some mass and cross section for cosmic ray upscattering and some mass and coupling for supernova upscattering that would give you similar event rates at similar points in the energy. So there could be some degeneracy there, but we're not, to the point of trying to identify particular bumps. We're just saying everything here could potentially be dark matter. Even if we do that, can we rule stuff out? And the answer is yes.
What about type 1A supernova? There's less mass ejected, but the velocities are higher. And if you're doing
Right.
V to the fourth or V to the sixth, they also may be producing this.
Yes, that's absolutely correct. And the reason we didn't think about that is just that monogem was the closest one that we knew of that had the right age and velocity. But you're absolutely right. And actually, we did initially model monogem as a type 1A supernova just to see what the limits would look like. And the limits are somewhat better, particularly at, you see how this exclusion region sort of narrows at high mass and this one goes away at high mass. If we model monogem as a type 1A supernova, this region extends much further over and this one stays wider. And the reason for that is that at masses of like a few GeV, hydrogen and helium can't really kick the stuff up to the high enough energies to see anything. You need it to be iron and oxygen and silicon. And for a type 1A supernova, the velocities of those heavy nuclei are high enough that you get a larger flux for this heavy dark matter. So in that sense, I can say if monogem was a type 1A supernova, you would get somewhat stronger limits. As far as looking for a specific type 1A supernova that you could redo this project with, I would need to go back through the lists of supernova remnants that we were looking at.
Also, why you put in this law?
Yeah, so it's partially because the limit here is just not very strong. It's deep underground, so there's a lot of attenuation, which means that there's only a narrow range of parameters of cross-section that you can probe. And if you look at this projection for the underground future super CDMS detector, you can see that like right around here, the exclusion region is significantly broader than it is over here or over here. So it's basically like take this exclusion region and just make the exposure not as good. You end up with a little blobby thing like that. Yeah, there are of course future plans for a next generation of PICO, but we didn't compute projections for that. Any other questions? I apologize if we went a little bit over time. Well, thank you guys again.
Can I tell you a story about sidereal time and solar time?
Yes.
I know radio astronomer is now deceased, and he grew up in